So let me start here. I wanted to start with this absolute value example. That's where we ended last time. And so before I get into that, let me just remind you of the definition of the absolute value function. So just to put everything in perspective, we first started talking about functions, which are input-output machines. And our rule for a function is for any input, there can only be one output. We can never send one input to two different outputs. So then we start talking about piecewise defined functions. And so here is where the absolute value comes in. This is a very famous, a very well-known piecewise defined function. You know, I personally believe that a substantial part of Calc 1 is just getting comfortable with the absolute value function and understanding how to work with it. So just to remind you, here's the definition. We use these weird vertical bars to denote the absolute value function, and it's a piecewise defined function. So, you know, what I think is important is to understand that this notation is really code for this definition. And we should, when we see the absolute value function, you should think of this as a compressed file, and we want to uncompress the notation. Anytime you see notation in math, you have to ask yourself, what does this actually mean? So here, for the absolute value function, it's a piecewise defined function. And here, you know, the way I want you to think about the definition is if the squiggle in between the absolute values happens to be greater than or equal to 0, happens to be non-negative, then you just copy down the squiggle that was in between. Just repeat the squiggle, just return the original X. If the squiggle in between the vertical bars is negative, then we copy down the squiggle in between the vertical bars and we add a minus sign. Okay, so this is the main idea. You know, I'm not obsessed with the fact that there's the variable X is in between the vertical bars. It's just, you know, absolute value of blah. And if blah is positive, just give me back blah. If blah is negative, write down negative blah. That's really how I'm thinking of the absolute value function. Okay, so let's take a look at this example. So this is the kind of example, you know, you're going to have to be able to like interpret this function. So specifically this absolute value function here, we should be able to decode that. We should be able to understand what that looks like. We should be able to graph it. Okay, so let me show you now how we go about this. So basically with the absolute value function, we basically need to know where the thing in between the vertical bars is positive and where it's negative. So in this case, we're specifically interested in this function here. We want to know when is x squared minus 2x, the thing in between the vertical bars. When is that greater than 0? When is that less than 0? The easiest way to find that out is to first figure out when it's identically equal to 0. So here I set the expression in between the absolute value bars, x squared minus 2x equal to 0, factor out the common term, and here, you know, the x times x minus 2 will equal 0 if x is equal to 0 or if x is equal to 2. And so now what I want to do is I want to just make a sign chart. So I want to make an x-axis. On this x-axis, I want to put down 0 and 2. So here's 0 and 2. And then I want to check the sign of the function. Is it positive? Is it negative? And so you pick values. Like to the left of 0, for example, I can pick -1. And then take that -1 and plug it in to the function. You know, it's easier to plug it in here. If you plug in -1, you get negative times negative. We see that the function will be positive here. So to the left of 0, we see that the function will be positive. Between 0 and 2, for example, choose 1. Take 1 and plug it in here again. You get positive times negative. So it's negative right here, the function. And then for the last one, for example, choose 2.1. Plug it in. You get positive times positive, so the function is positive here. So now that we know where the function is positive and negative, I can now use the definition, right? So I'm going to switch over here to the document camera for a second. And so let me show you how this works now. So here's how I think of the absolute value, right? The absolute value of blah is equal to, so the absolute value of A, if A is positive, if blah is greater than or equal to 0, you just return the same expression. The absolute value of A, if A is negative, you return A but put a minus sign in front of it. In this case, the function we're looking at is x squared minus 2x. That's the A. Here, x squared minus 2x is A. So now think of this whole expression, x squared minus 2x. Think of that as a single, variable called A. And now I need to know where's A non-negative and where's A, where's A negative and where's A, non-negative and where's A negative. And that's when we set it equal to 0. We found the roots and we plugged in and got the number line. So I know x squared minus 2x is positive when x is less than 0. And I know it's positive, or I should say non-negative. It's greater than or equal to 0 when x is less than or equal to 0. And it's greater than or equal to 0 when x is greater than or equal to 2. So in that case, when the function is non-negative in that region, I just copy down the function. So here I just copied down whatever was in between the vertical bars where it's positive. And where it's negative, I copy down what's in between the vertical bars, but I put a minus sign in front. And so using this basic definition, by keeping track of where it's positive and negative, I'm able to write down the piecewise definition. And so that's where I get this expression from right here. So here, that's where this expression comes from. Absolute value x squared minus 2x is x squared minus 2x if x is less than or equal to 0 or if x is greater than or equal to 2. And it's negative x squared minus 2x if x is between 0 and 2. This is exactly the region, where the function is negative, between 0 and 2. So there's this clear correlation between where the function is non-negative and how we've defined our absolute value. And then finally, I distribute that minus sign just to simplify everything, just, because we're nice people. So distribute the minus x squared plus 2x, which I wrote as 2x minus x squared. So being able to go from this step up here, this function up here, to this definition down here, that's crucial. That's really important. That's something we have to be able to do. And so for the graph, the way I always graph things with the absolute value is first, I try to figure out what would the graph of the function without the absolute value bars. So here I've removed the absolute values here. First, let me just try and figure out how to graph this function. Now, folks, x squared, so it's a parabola. It's an upward facing parabola because the coefficient of x squared is positive. And we also know that its x-intercepts are 0 and 2. So I know that this, so let me now, here, let me put an axis here. Whoops, let me change color. Okay, so let me put an x and y axis. There's my y axis. There's my x axis. So I know this is a curve. This is a parabola that goes through the point 0, here's 0, and it goes to the point 2, and now it's an upward facing parabola. So now I'm just going to sketch a parabola that's upward facing that goes between these 2 points. Yes, I know. I should have been an artist. I know. I hear it all the time. Wasting my time doing math. I know. Okay. But now this is the graph of the original function. For the absolute value, what I need to do is take any part that's negative and reflect it above the x-axis so it's positive. So that now this will now be the graph of the absolute value. And so that's what I have down here. If you look, this graph with the dotted line down here, that's the original parabola without the absolute value. And then with the absolute value, I flip the section that's below the x-axis above the x-axis. So this example is an important example in terms of working with the absolute value. And this is the kind of thing we should, be comfortable with. And certainly practice makes perfect. So let me talk about symmetry. And so symmetry has to do with the shape of the graph relative to the y-axis and x-axis. And we have two types of symmetry. A function can be even, so even symmetry, or a function can be odd. Or a function could be neither. So a function does not have to have symmetry. So here's the definition of what it means for a function to be even. So there will be a geometric implication. So when we say a function's even, what we mean is it's symmetric about the y-axis. So this is one description of what it means for a function to be even. But in math, what we're really trying to do is we're trying to get the part of the brain that works with equations to interact with the part of the brain that works with images. It's called left-right brain interaction, and mathematicians typically have the highest incidence of left-right brain interaction. It just makes us better thinkers. So here, I want you to also focus on the definition, the analytic definition. So a function is said to be an even function if and only if f of negative x equals f of x, okay? So if we were to draw a picture, f of negative x equals f of x, here would be one example. Think about what we're saying here. If I pick some point, let me write down here, call it x. And if I pick another point that's the same distance away from the origin, but on the other side, negative x. Remember, x and negative x are our inputs. Then a function is even if we put x and negative x into the function, the outputs are the same. Here, if you look at the output, the outputs are the same. For any input you pick, if you pick if you reflect that, if you pick the same input on the other side and plug it in, you get the same output. And so we really want to connect up both ideas, folks. This definition along with a working example. Typically with every definition, you should have an example that goes with it. So this is the function f of x equal to x squared. I'll show you in a second. I'll prove that it's an even function. Here, we'll do an example in 1 second. The other type of symmetry is known as odd. You could have odd symmetry. So a function is said to be an odd function. So here we have a function is said to be an odd function. And again, here's the analytic definition. If f of negative x equals negative f of x, look at where the minus sign is compared to the definition for an even function. And here, when we say a function is odd, it has symmetry about the x and y axis. So what do I mean about symmetry? So here, if I took this function and reflected it about the y-axis and then reflected it about the x-axis, you get back the same function. For an even function, if I take the function and reflect it about the y-axis only, if you get back the same function, then that's called an even function. And so, as I said, the analytic definition is really important, as well as the picture that goes with it. These, typically when I learn a concept, I try to learn the concept plus an example, a tangible example to go with it. And here, x squared is my favorite example of an even function, and x cubed is my favorite example of an odd function. So let's prove f of x equal to x squared is an even function. We would prove it using the analytic definition. So I'm going to start with f of x, and I'm going to replace this x right here with a negative x, okay? And so think about what f of negative x looks like. F of negative x, put parentheses around the negative x. You want to put parentheses around the negative x and square that. F of negative x looks like negative x quantity squared, the whole thing squared. The big mistake I want you to avoid is some people will write, and it's kind of a natural mistake to make, that f of negative x equals negative x squared. They'll put the minus sign outside. But remember, here, the minus, you replace this x gets completely replaced with the negative x. So the negative has to also be squared. So you know, be careful, writing this is wrong. And this is not an uncommon mistake, it's a natural mistake to make. But remember, the minus has to also be squared. So minus x squared, minus x times minus x is just x squared. But x squared is exactly the original function we started with. So f of negative x equals negative x quantity squared, which equals x squared, which gets us back to f of x. So we've shown this definition has been satisfied. So I can conclude f of x is an even function now because the definition has been satisfied. And for x cubed, we do similar manipulations. So if you look at the function f of x equal to x cubed here, again, I start by replacing the x with a negative x. So the x gets replaced with a negative x. Now you multiply negative x to itself 3 times. You get minus x times minus x times minus x. You get minus x cubed. 2 of the minus signs cancel out, but there's still one more minus sign. And remember, in this case, x cubed is our function f of x. So negative x cubed is actually the same as negative f of x. So again, you know, we've satisfied the definition. From here, we've shown, this definition here is satisfied. So I can conclude the function is an odd function. And certainly if you graph it, we see the symmetries, you know, that we expect from an even and odd function. So as I said, I like to learn a concept and then have an example to go with it, you know, so that it's not abstract. 2 very well-known functions are cosine and sine, and we can use trig identities to show cosine is an even function. So I don't know if you remember, we have these sum and difference identities, like cosine a plus b equals cosine a, cosine b minus sine a, sine b, that type of thing from pre-calculus. I'll let you look, it's in your front cover of your book. But using those identities, we can prove cosine is an even function, and we can prove sine is an odd function, okay? And those are now common knowledge facts in this class. Cosine's an even function, so cosine satisfies this equation, and sine is an odd function, so sine satisfies this equation. So if you have sine of negative x, you can pull the minus out, which is kind of handy. The other thing I want to talk about are increasing and decreasing functions. So again, I want you to connect up the picture with the definition. We're doing left brain, right brain training right now, okay? So a function is said to be increasing on an interval if and only if, and so here's the definition we want to think about. A less than B implies f of A is less than f of B. So here's where I now want you to look at let's look at the picture, okay? So first thing is, so we're looking at this picture here. We're looking at the picture from left to right. That part is really important. Otherwise, none of this is going to make sense to you. We must look at the picture from left to right, okay? So now here, if you look at this left to right, I've drawn a graph that's increasing. What we expect when you say increasing, if you're looking at it from left to right, is a graph that goes up. So that's what we have here, a graph that goes up, something that's increasing. So now let's check the definition. The definition says, if A is less than B, so here's A. If A is to the left of B, that's what A less than B means, right? If A is to the left of B, then now let's see what happens with the output. So if you follow A, here's f of A. And if we follow B, here's the output for B. Yeah, so you see for an increasing function, if A is less than B, then f of A will also be less than f of B. You see f of A here is below f of B. So it's not complicated, but what I need you to do is connect up these two things. Understand how these equations and this picture match up and how you get one from the other. And similarly, we have a decreasing function. So a function is said to be decreasing on an interval if and only if. And so here's the analytic definition, the definition that does not use the picture. You know, for me personally, I hate the picture. I only like the analytic definition. I like to do everything by formula. So I work really hard to try and understand the picture. I work at the things I'm not good at because that's the only way I'm going to get better. So here's the picture. Looking at it from left to right, we expect the decreasing function to go down. That's exactly what we have here, a decreasing function that goes down. So now let's check the definition. It says if A is less than B, so if little a here is to the left of B, which it is. Now let's follow the output. Then f of A, so let's look at f of A here. So I go up here, and then I cut across. So here's f of A. And here, let's follow f of B. So here I go up to the function, and then over here. So here's f of B. So look, you see for a decreasing function, if A is less than B, then f of A will be greater than f of B. And again, you know, what I really, really want you to do is match up the picture and the analytic definition. We want, you know, left side of the brain and right side of the brain to be connecting these concepts, okay? So quick example, you might have to look at it a couple times. It's not difficult. You've probably done stuff like this all the time, but we don't usually think about increasing, decreasing functions when we do this. We just think of this as properties of inequalities, but it's really because of increasing, decreasing functions. So here's the question. We're given that x is between 1 and 2. Okay, so that's what we're told. If x is between 1 and 2, we're asked to show that the square root of 1 over x cubed will be greater than 1 over 2 root 2 and will be less than 1. Okay, so this entire problem is entirely an exercise in increasing, decreasing functions. Let me show you. Starting with x between 1 and 2, I claim that you can cube everything and not change the direction of the inequality. So here, how do I know if x is between 1 and 2, then x cubed is between 1 and 2 cubed? Well, because x cubed is an increasing function. So let me draw the graph of x cubed. So you remember the graph of x cubed looks something like this. Holy moly. That's horrible. Let me try that again. See, it was okay until the end. Yeah. Oh my God. All right, last time. I'm gonna get in at an angle here. Okay. X cubed, that's as close as I'm gonna get. All right, use your imagination. So now look, pick a point A. Look, if I pick some point A right here, or actually, let me just call it 1 because we picked 1 and 2. So here's the number 1. Here's the number 2. Here's x. If you follow x cubed, look what happens here now. If I follow x cubed here, this goes up here, then this goes here. This goes up here to the function, and then this goes here. So I have my 1 cubed is right here. This is 1 cubed. This is 2 cubed. And look, the function x, if you follow the variable x, ends up right here in between. So if x is between 1 and 2, then x cubed will be between 1 cubed and 2 cubed. And this is completely because x cubed is an increasing function. And now I need a reciprocal. So if you look here, the x cubed is in the denominator actually. So I'm going to take a reciprocal. You know, when you take a reciprocal, the inequality changes direction. The reason is because the reciprocal function is decreasing. Do you remember your 1 over x function, what that looks like? The graph of 1 over x is a decreasing function. Look at it left to right. Look at it left to right. It goes down. So you pick a, pick a b. Then if you apply the reciprocal, look, 1 over a. So here a is less than b, but 1 over a is greater than 1 over b. And you know, you learned that rule in pre-calculus. So when you take the reciprocal or when you multiply by a minus sign, you change the inequality. That's because the reciprocal is a decreasing function, and the function y equal to negative x is also a decreasing function. So when you multiply by a minus, you change, or when you take a reciprocal, you change the direction, because we're dealing with increasing, decreasing functions, decreasing in the case of reciprocal. Finally, I need a square root. If you look here, there's a square root here. So finally, I have to take a square root. And you remember the graph of square root. It's an increasing function, right? So that's my y-axis. This is my x-axis. The graph of square root looks like this. So here, I can apply the square root. I don't have to change the direction of the inequalities. So now if you compare this and this are the same. I'll let you look at that closely, but these are the same now. And we're finished with this example. And this was, you know, all about the increasing and decreasing functions. And very shortly in Calc 1, but also in Calc 2 and Calc 3, we will have to do math that involves inequalities, not equalities. In life, there's more inequality than equality, right? So we will end up doing more math with the math of inequalities. That involves understanding increasing and decreasing functions. All right, gang, that ends section 1.1. So now I'm going to switch over to section 1.2.
Professor, I have a question.
Yeah, go ahead.
Yeah, how were the two statements from before equivalent? I don't really get it.
Which two statements?
The 1 over 2 square root of 2 and the result that we got. So how is 1 over, yeah.
This is the same as this?
Yeah, how?
Because square root of 8 is the square root of 4 times 2.
Oh, I got it backwards. I see now.
And then the square root of 4 is 2, right?
I see. Yeah.
Cool?
Yeah, thank you.
No, thank you for that question. So, all right, folks, good questions. We really need to make sure we understand all the details, right? That's during the test. That's where mistakes happen, when we don't know about the little details. So I'm really glad for that question. Okay, folks, I'm going to switch over now to the lecture for section 1.2, which I emailed you yesterday at 12:24, because that's the kind of wild stuff I do. So here's function families, section 1.2. Everyone, don't get too excited all at once. Calm down, please. Thank you. I saw some mayhem going on. So this should basically be a review for you, but you know, let's review and let's really make sure we understand the details. So here we introduced to you the basic shapes of functions, and these, you know, you should memorize. You should know these basic shapes. And how are we figuring out the basic shapes? Basically, some human at some point plotted points. They took inputs, calculated what the output looks like, and plotted a bunch of points and figured out the basic shapes. And so I've basically done the same here, but using a computer. I've asked the computer to plot points. The computer here is maybe plotting 100 to 200 points. Humans are much faster, much smarter, I should say. We can figure out the graphs by plotting a few points and using our knowledge of geometry and calculus. That's what we'll work up to. Using a few equations and plotting a few points, we'll be able to find the graph, whereas the computer has to plot hundreds of points. So y equal to x, as you all know, is a diagonal line through the origin. Y equal to x squared is the upward facing parabola. Y equal to x cubed is the graph I failed so miserably in trying to reproduce just now. This function here, a lot of people call this the square root function. That's actually a bit imprecise. This function here is actually the positive square root function. Okay, and I'll come back to this in 1 second and talk about this a little more. That's why I wanted to emphasize that there's actually a plus symbol here. Usually when we say the square root, that refers to both roots, the positive and the negative root. That's why to call this the square root is a bit misleading, because it only is giving us the positive root. I'll come back to this in 1 second. We have the cube root of x. We have the reciprocal function y equal to 1 over x. We have cosine of x. We have sine of x. And then we have absolute value of x. Other important functions that we will get later on is the exponential function e to the x and the natural log function ln of x. But in our class for right now, we don't need to worry about those functions. To define those functions, we actually need calculus. Okay, so those functions technically cannot exist without first doing some calculus. So let me talk about the square root function. And let me switch over to the document camera, and let me explain my whole issue with, there's a little bit of imprecision in the language that can cause confusion. So here, in general, when we talk about the square root of a number, we're referring to both roots. So for example, if I say the square root of 4, the square root of 4, what I'm referring to are both roots. I'm referring to plus and minus root 4. And plus and minus root 4, look, there's two answers here. There's a plus root 4, which we write as 2, and there's a minus root 4, which we write as negative 2. Now here's the problem. Humans will write the plus root 4. We will also just write it as root 4 without the plus symbol. Now you have to be careful. There is a plus symbol there, and this is the positive square root. This is a positive square root. So to call this function here just the square root is going to cause confusion. And what a lot of humans do is we drop off the phrase positive when we're referring to this function, and that's wrong. Down here with the negative square root of 4 is equal to negative 2. This is the negative square root. So the square root is actually made up of two separate functions. The square root is made up of a positive square root and a negative root function. So here's the big mistake I see. So here's a common mistake. So what I'm about to write down is incorrect. So a lot of students will write this. That is wrong. What is correct is if you just write the radical symbol in 4, you should just get back 2, because that's asking for the positive root. Okay? But if we have an equation, if I have x squared equal to 4, in this case, I'm looking for all numbers that satisfy this equation. In this case, if x squared is equal to 4, in this case, it's correct to say x equals the square root of 4, which is plus or minus 2. But if you just have this symbol by itself, root 4, that's not equal to plus or minus 2. Root 4 by itself is just equal to 2. Root 4 is the same as the positive square root of 4. Okay, so we tend to be a little bit imprecise with the language, we tend to refer to this function as the square root, but the square root is actually two roots, not just one root. All right, folks, I don't know if you like that or not. Are you with me? Are you okay? So here, and even I'll do it. Even I will refer to this function right here as the square root. And that's wrong. The square root actually looks like this, right? If you talk about the square root, actually looks like this. The square root should have the positive roots as well as the negative roots. The square root is not a function. And here, what we've written here is just the positive part. So this function is actually the positive square root function. Very few people call it that. They just call it the square root. But let's understand what's actually happening. And keep in mind, there should be a plus symbol right here. And dropping the plus symbol, I don't know that necessarily helps us, because that's what leads to confusion. Okay, so please be careful. This is only giving us the positive roots. This is only giving us the positive roots. This is the positive square root function. Okay, and then if you flip this over, put a minus sign in front of it, then you get the negative square root function. Okay, so let me talk about classes of functions. Here, when you see a function, you should really try and classify it. Just like if, we try to classify different species of fish or whatever, if you're going fishing, I caught a trout or I caught a marlin. I don't know if trout and marlin are in the same bodies of water, but whatever. So here we have polynomials. You know what a polynomial is? It's a number multiplied potentially to a variable where the variable is raised to an integer. The variable could be raised to 0, and you can have a sum or difference of more than one such term. Here's the generic form for writing a polynomial. So take some time to look at this. And the main things, when you look at this, what I want you to immediately identify. First, you should say that a sub 0, a sub 1, a sub 2, up through a sub n, these are all constants. And then the other thing you should immediately identify, the only variables here are the x's, x squared, x to the 9th. These are the only variables. Remember, a sub 0 is being multiplied to x to the 0. So always make sure you know your apples and oranges. Which are the constants? Which are the variables? A quadratic polynomial is specifically a second degree polynomial. Typically, we write it in the form ax squared plus bx plus c, where a, b, and c are real numbers. Remember this notation? We introduced it last time. This is, in English, we would read this sentence as a, b, and c are elements of the set of real numbers. Another way to say that is a, b, and c are real numbers. Or, a, b, and c are real constants is another way to say that notation. It's important that you start converting the written symbols into full English sentences. Don't just read the math, interpret it, right? So in my mind, I don't say a comma b comma c element r. I say a, b, c are real numbers when I look at that notation. Now, if you take two polynomials and take their fraction, we get what's called a rational function. Rational, like the word ratio. So when you see the word rational here, you should think the root word is ratio, like a function. Okay, and of course, we require the denominator be non-zero. Root functions. So this is a function of the form x raised to 1 over n, where n is a positive integer. For now, n is a positive integer, but very soon we will allow n to be any real number. Okay, so starting out in the theory, it starts out as a positive integer, and then calculus actually allows us to extend it to be any real number. Most people don't keep track of those kinds of things, but I'm a math teacher, so I kind of like to. Finally, I want to mention trigonometric functions, sine and cosine, tangent, those functions. These are examples of very important examples of what we call bounded periodic functions. A bounded function is a function whose range is finite. So sine and cosine only oscillate between -1 and 1. So that's why we call this a bounded function. And the periodic part, that refers to it repeats itself. So the periodicity, this refers to the fact that after every 2 pi distance on the x-axis, you get the same y value, right? For cosine or sine, after 2 pi, you get the same y values repeat after every 2 pi of distance on the x-axis. So bounded means the range is finite, and periodic means the function repeats itself, and cosine and sine are very, very famous examples of bounded periodic functions. I want to talk about some basic transformations of functions. So this involves shifting and reflecting. So starting with a positive number. Okay, so be careful here. I'm assuming c is greater than 0. If we add c to the range, okay, what do I mean to the range? I'm adding it to f of x. I'm not adding it inside the parentheses to x. So think about where the plus c is happening. Here we're adding it to the range. And if you add a positive number to the range, it pushes the graph up. If you subtract a positive number from the range, it pulls the graph down. So here I have two examples. The graph y equal to x squared is the original graph right here that I'm starting out with. And then in one case, I add 3, and you can see that pushes all the points in the range up 3 units. And then in the other case, I'm subtracting 3, and you can see it subtracts 3 from all the points in the range of the original function. They all get 3 subtracted. So the whole function shifts down by 3 units. Now, if we add the constant inside to the domain variable, look, I want you to pay attention as to where this subtraction is happening versus where this is happening. In number 2, we have f of x minus c. In number 3, we have f of quantity x minus c. So here, we are doing the subtraction in the domain right here. This is in the domain. So here it says it shifts the graph to the right. You know what's actually happening when we do x minus c, when c is positive? It moves the x-axis to the left. But we live on the x-axis. So we don't notice the x-axis moving. Instead of us noticing the x-axis moving to the left, what it looks like to us is the graph moving to the right. In fact, we're moving to the left. Okay, so that's why it's opposites. X minus c shifts the x-axis to the left, so it looks like the graph is shifting to the right. And similarly, if you do x plus c, where you're adding the c to the domain variable, that's going to shift the x-axis to the right, but we live on the x-axis, so to us, it looks like the graph is moving to the left. You know, when in fact, we're moving, but we live on the x-axis, so it looks like the graph is moving. So here you have an example of the shifting. Again, the base function I started with is the parabola y equal to x squared. That's right here. And in one case, I'm adding 3. So that gives us this left shift, or the axis shifted to the right. And then in the other case, I'm subtracting 3. And so that causes a shift here to the right, or the x-axis moved to the left. And so this is our basic shifting here, which you've seen before. And combined with the basic shapes and plotting some points, you can figure out which way the shifting goes. At the end of the day, you can always plot some points to figure out exactly where your curve is oriented. So here we're using a combination of techniques. We're analyzing the shape, we're thinking about the symmetry, we're using our knowledge of shifting and translations, and then we're plotting some points. It's synthesis of information, taking many facts and putting them together to come up with one conclusion. We have stretching and reflecting. This is what you do every morning when you wake up, right? You stretch, and then you reflect, right? You reflect on your day, on what you're going to do. So here, we're interested in what happens when you multiply or divide a function by a constant. In the previous slide, we were adding or subtracting a constant. And again, here we want to know what's the effect when you multiply or divide to the range variable. What's the effect if you multiply and divide on the domain variable? So here, again, I assume c is positive. If c is greater than 1, and you multiply c to the outside of the function, to f of x, then that's going to cause stretching in the vertical direction. That means you pull it up and down. We're pulling in the up and down direction. If c happens to be less than 1, and we multiply it to the outside of the function, then we get compression. You push it down in the up or down direction, in the vertical direction. So here I have an example of the original function, again, is x squared. In the dashed line down here is our original function x squared. And I've multiplied the range element by 2. And so you can see the effect is every y value gets shot up. You know, its value is effectively doubled, right? So some y value that was down here has now been pushed up. Y value that was down here has now been doubled and pushed up. But 0 doesn't move. 2 times 0 is still 0. So the curve is still anchored at the origin. And so it's anchored at the origin, but all the y values are moving up, so it gets stretched. Because it's stuck at the origin, but it's being pulled up, so it gets stretched. In the next example here, I multiply by 1/2. Again, keep in mind, the dashed curve is x squared. The dashed curve in both graphs are the same. In this case, when you multiply by 1/2, the y values get reduced by 1/2, the original y values. But 0, 1/2 times 0 is still 0, so that's still stuck there. So it's being squashed in the vertical direction. Now, here we were multiplying to the range variable. If we multiply inside on the domain, so here, look where the c is compared to where the c is here. In number 2, we're multiplying the domain variable by c. In this case, instead of causing compression in the vertical direction, this causes compression in the horizontal direction. If c is greater than 1, it'll be horizontally squashed. And if c is less than 1, then it'll be horizontally stretched. In the horizontal direction, you pull it. And again, we can determine the exact effect of the scaling. So when you multiply or divide by a constant, either the range or the domain variable, that's called scaling. We can determine the effect of the scaling by plugging in points. You know, ultimately, we put all of our knowledge together: shape of the graph, symmetry, increasing, decreasing, stretching, reflecting, translation, and then plot points and try and get a picture of what the graph is doing. I didn't do an example for number 2. And here in 1 and 2, the constants were positive. What happens if you multiply by a minus sign? If you multiply the range element, if you multiply on the outside by minus, it's going to make anything that was positive negative and anything that was negative positive. So a multiplication by minus sign on the outside causes a reflection about the x-axis. So if it's above the x-axis, it'll be below. If it's below, it'll be above. If you multiply the domain element, the x variable, here it takes any x that was positive will now be negative, and any x that was negative will now be positive. So it's literally flipped the graph around. The positive x's flip around, the negative x's switch. So it literally reflects the x-axis, the graph about the y-axis. So here I've given a graph of multiplying x squared by negative on the outside. Remember, for x squared, it's symmetric, so multiplying the domain variable on the inside by my minus sign is not going to change anything because it's an even function. It's equal to itself. But if you multiply the outside, the range variable, by a minus, it makes our formerly positive parabola now a downward facing negative parabola. All right, gang, I'm going to stop right here.